Hello everyone. In this lecture, we will continue the study of the binomial coefficients. More precisely, we will study the multinomial coefficients theory, and then we turn to the Sperner theorem, which discuss the relation between the so-called trains and the antitrains. Firstly, we recall the binomial theorem. So if you have x plus y to nth power and do the distribution law, we will have the summation for k from 0 to n, and choose k times x to k's power, y to n minus k's power. And a natural question is, how about linear function or three variables? For example, if we have x plus y plus z to nth power, then if you do a similar thing, you expect a summation of a k1, k2, k3 times x to k1 times y to k2 times z to k3, and where k1, k2, k3 satisfy the relation, the summation is m. Okay, then question is, what is the exact value of the coefficients a, k1, k2, k3? And more generally, if you have x1 plus x2 all the way to xt and raise it to nth power, and then by the distribution law, we should have a summation and then the question is, what is the coefficient a, k1, k2 to kt? Okay, so the theorem gives you the following nice formula. So on the left hand side, just a power function, and on the right hand side, you have a summation for all ni satisfy summation is n, and each one is a non-negative integer, and then coefficient is n factorial divided by n1 factorial, n2 factorial, all the way to nt factorial. And then you have the monomial parts, x1, n1, x2, n2, all the way to xt to nt. And here actually, this is what we, and it's just like n choose n1, n2, nt. Okay, and for the proof will be very similar to the proof for binomial theorem. I just give you some hint. The first proof is so-called combinatorial argument, just like you write down the power function as a product of n factors. Okay, and if you want to know the coefficients of, for instance, x1, n1, x2, n2, xt, nt, then it's equivalent to count how many x1 to n1 all the way to x2, nt appear in when you do the expansion. Okay, then this is same as choose n1, x1, n2, x2s, nt, xt's from the product. From the product data. Okay, then it's easy to see, just like to count how many combinations you have. So therefore, the answer is n choose n1, n2, all the way to nt, which is n factorial divided by n1 factorial, n2 factorial, all the way to nt factorial. Okay, and then the second proof, of course, if you want more mathematically rigorous one, we can mimic what we did for the binomial theorem. That is, we use a Pascal equality. And I will not repeat. So the idea is induction based on Pascal-like equality. So what is Pascal-like equality? So that is the following lemma. Suppose you have non-negative integers n1 to nt, and we let n to be the summation of all the ni, and then for n choose n1 to nt, we have it equals n minus 1 choose n1 minus 1 n2 to nt plus n minus 1 n1 n2 minus 1 all the way to nt, and plus all the way to n minus 1 n1 n2 nt minus 1 nt minus 1. Or if you want a concise form, there will be summation for I from 1 to t, n minus 1 n1 n2 all the way to ni minus 1, then ni minus 1 ni plus 1 all the way to nt. To prove this, you can also use induction argument. Okay, I will not repeat. Okay, next we turn to another interesting topic, which is called Sperner theory. So the starting question is, we want to know what is the largest number of subsets from 1, 2, 3, 4 all the way to n, with some sets from we can choose such that none of them contains another. And here is an easy construction which leads to a lower bound for the number. Let's call this number capital N. So define AK to be all the subset S of 1, 2, 3, 4 all the way to N, such that the cardinality is K. Then it's easy to see that there n choose k element in AK, and by unimodality of binomial coefficients, we know that for all k, the cardinality of AK takes the maximum when k is n over 2 floor, or when n is odd, you have another choice, that is n choose n over 2 ceiling. Therefore, and noted that for all two elements x, y, or let me see, let me use S1, S2 in AK. S1 cannot be a subset of S2, and S2 cannot be a subset of S1. Therefore, we construct at least as many as n choose n over 2 floor sets. So capital N has a lower bound like this. In the following, we are going to prove that actually this is sharp. Remark. We will show that this bound is sharp. Okay, to do this, we generalize or introduce some convenient concept. So suppose you have a collection KLC of subsets of S, and we call this is a train, provided that for each pair of subsets in C, one is contained in the other. That is for all A1, A2 in C, and A1 different from A2. Oh, actually, we don't need this condition. For all A1, A2 in C, either A1 is a subset of A2 or A2 is a subset of A1. And to get some feeling, let's look at the following example. Suppose you have a set of 5 elements, and let's C1 to be a collection of 3 subsets, 2, 2, 3, 5, 1, 2, 3, 5. And then it's clear you have a linear inclusion relation. 2 is a subset of 2, 3, 5, which is a subset of 1, 2, 3, 5. And if you let C2 be a collection of subset, empty set, 3, 3, 4, 1, 3, 4, 1, 3, 4, 5, 1, 2, 3, 4, 5. then you can verify that C2 is also a train. More precisely, we can represent the train by the following inclusion relation. Empty set is a subset of 3, which is a subset of 3, 4, which is a subset of 1, 3, 4, contained in 1, 3, 4, 5, contained in 1, 2, 3, 4, 5. Okay, and a small remark is for convenience, in the following, we will use the inclusion relation or inclusion relation to represent a train. That is, suppose you have a subset, you have a collection or subset C, which is A1, A2, AM, and A1 is a subset of A2, subset of AM. We will write the train. We will write the train C as just as A1 containing A2 containing AM. So that's why we call it a train. I would actually here I use implicitly the following property, that is, if C is a train, we can always let's see, A1, A2. We can always assume that A1 is containing A2, containing A3, containing AM after rearrangement of the indices. This is actually not that not that obvious, because at the very beginning you don't know if you can put all the things in a train. This is just like a total order. So actually you need to prove this. In the notation we introduced the last time, this actually is a total order, but at the very beginning we didn't mention that, so you need to prove this, although it's easy. Okay, and another very important concept is called a maximum train. It's just like a maximum element, so we will define it carefully. So let C be a train. And we call it maximum if there doesn't exist an integer k between 0 and m-1 and a subset y of S such that ak is a pure subset of y which is a pure upset of AK plus 1. So, i.e., AK is a subset of Y, is a subset of AK plus 1, and Y is different from AK plus 1. So how to understand it? So we can understand in this way. We cannot squeeze any other subsets into the train A0 containing A1 containing all the way to AM. Okay, and now let's look at some example. Suppose S is a subset, is a set of n elements. And C is defined by, okay. Let's see, empty set contained in 1, contained in 1, 2, contained in 1, 2, 3, all the way to 1, 2, 3, 4, to N. Okay, so this is your A0, this is A1, A2, A3, to AN. And noted that here AI, the magnitude of AI, the cardinality of AI is I, and the cardinality AI plus 1 minus cardinality of AI is 1. Okay, and the remark 1 is the maximum train is not unique. This is just like for an arbitrary set with some order, the maximum elements usually is not unique. Okay, and secondly, although the maximum trains are not unique, but we have some common properties shared by all the maximum trains. For example, for any maximum train, in this problem, in this example, we have the cardinality of AI is I. Okay, and a natural question is, then we would like to know how many trains S in total. Probably this is still a very hard problem. Then we turn to a slightly easier one. How many maximum trains of S in total? Okay, and this is easier to answer and has a very nice structure. You can even count the cardinality. You can count a number. Okay, so how do we deal with that. Suppose C is a maximum train. Okay, and then we can define let I1 be the element of A1, get rid of actually A0 actually is an empty set, but for the consistency we still write in this way. And define I2 be the element of A2, get rid of A1. And lastly, let IM, which is actually IN, be the element of AN, get rid of AN minus 1. Actually here, also a remark, you can prove M is N. Okay, for each maximum train, you can do this construction. It turns out that this construction gives you a bijection between maximum trains and the permutations, that is I1, I2, all the way to IN. Okay, in particular, so property 1, so how totally we have n factorial maximum trains. And secondly, from this construction, we can even have a better understanding of the maximum train. So for example, let S theta be a subset of S theta, and let n S theta be the number of maximum trains containing S theta. Then actually we can compute n S theta as follows. It's k factorial m minus k factorial. Okay, so why this is true? This is because, so a short proof. So for each, also here, sorry, here K actually is a kinetic of S. So take any maximum train, AK plus 1, AK minus 1, all the way to AN. And here AK actually is S theta. Then each maximum train, C, Cal C, corresponds to a pair of trains. So first one is A0 containing A1 all the way containing AK minus 1 containing S theta, and then you have S theta equals AK containing AK plus 1 containing all the way to AN. And actually this correspondence is a bijection. So when you do a combinatorial argument or construct some bijection transform one object into another one, the most important thing is you really need to verify it's a bijection. It's one-to-one and onto. From your homework, we can see some people made a mistake when they do the construction. Okay, and so first one, just like you choose a maximum train in X in the set S theta. So totally you have K factorial maximum trains. And then the next one, just like choose trains in so maximum trains in S get rid of S theta. So here is the maximum trains in S theta. Therefore, here totally have n minus k factorial maximum trains. Okay, and then you do the product. We have n S theta equals k factorial times n minus k factorial. Okay, and next very important concept is called antitrain. From the definition, you will see antitrain just means it tries to destroy as many as train relations as possible. And then later on, from our description of the relations between train and antitrain, you will see actually antitrain also has a dual version, can be viewed as a dual version of the train. Okay, so an antitrain Chi C is a collection of subsets of S such that for all x, y in this collection, x is not a subset of y, and y is not a subset of x. So the remark is there's no inclusion relation. So if we draw a picture, probably then we will have a better understanding. So suppose you view all the subsets as some vertices, and you join them by lines when you have inclusion relation. And the train in some sense means that as many edges as possible. So we'll see actually here will be, for example, the train has 5 sets, T subsets. then the relation is t choose 2. That will be the maximum edges appear between t elements, t vertices, and then an antitree. So as less edges as possible. So that will be 0. Okay, so you will see this just two extremes when we consider the relations, inclusion relations between subsets. And the following theorem is due to Sperner. That answers our question at the very beginning. Let's look at it just here. This gives you answer that actually n is n choose n over 2 flaw. More precisely, an antitrain on S contains at most n choose n over 2 flaw sets. So the proof. So how to derive this idea? So the idea given in your textbook is like this. So we try to, let's see, idea. We try to embed the antitree into maximum trains into the set of maximum trains. So for example, here is here is an antitrain. You have sets, for example, x1, x2, whatever. And then we want to construct an embedding into the set of maximum trains. So it's A maximum train, B maximum train, blah, blah, blah. The reason is that by the previous propositions, this one, 1 and 2, we have a better understanding of maximum trains. That's a typical idea we use in mathematics. When you want to give a bound for something, you compare it to some easier or relatively understandable object. So actually, give a bound is already one of the way we can compare something to some easily understandable things. 1, 2, 3, 4, all the integer numbers we understood well. They are sets. So how to compare, how to understand the relation or the information of a set? We take the cardinality and compare it to integers. That's already, we already use the idea implicitly. Okay, then as soon as you have this idea, then you can read the proof quite easily. So let Kyle A be an antitree and define Kyle AK to be a subset of Kyle A, which contains all the subset of S with K elements. And then it's easy to see, so K is from 0 to N. Then it's easy to see the antitrain has a partition or can be decomposed into n plus 1 parts. It's a disjoint union of AK for K from 0 to N. Okay, also we use Kyle B to denote the set of all maximum trains. And then, in particular, the cardinality of Kyle B is n factorial. And now, how to construct the embedding. So for element x in A, define Bx, which is a subset of B, contains all the consisting of all the element of B, all the maximum trains contains X. And most importantly, since Kyle A is an antitrain, then for all x, y in Kyle A, Bx intersect Kyle By is empty. Also here we also need to assume x is different from y. So this is because otherwise x is in a maximum train, x, y are in the same maximum train, and hence x is contained in y, or y is contained in x, which is a contradiction. Yeah, actually, then if you go back to the idea we illustrated before, so what do we do? Sorry. More precisely is as follows. For each object in the antitree Kyle A, we associate with a bunch of elements in the set of maximum trains. So those elements are the maximum trains contains X. The whole set is denoted by Bx. Similarly, here Y is embedded into Kyle B, and the inside you consider it maps to all the maximum trains containing Y. Okay, then if you want to estimate the magnitude of A, we try to understand in terms of the magnitude of chi B, magnitude of chi Bx, magnitude of chi By, blah blah. Okay, so more precisely, noted that since we have partition, the kinetic of chi A is a summation of for k from 0 to n, kinetic of chi AK. We call it chi because, when you use LaTeX, you use MySQL A to type in this chi A. Okay. Okay. On the other hand, the kinetic of beta, OB is at least as many as the kinetic of the disjoint union of Bx. So this inequality is because there might be maximum trains which contains no element in chi A. That's why we call it embedding, because you miss something. For example, if you look at picture, there might be some maximum trains, no pre-image. Okay, therefore you have the greater than or equal sign. And then for this set, since you have disjoint union, we can counter cardinality quite easily. So that will be the summation of chi Bx, the cardinality of chi Bx. And we also compute this before by the proposition 2 here. Okay, so this will be exactly kinetic x factorial m minus kinetic x factorial. Okay, then let's count how many. Let's plug in the property that chi A is disjoint union of chi AK. Then here the summation can be written down as follows. Summation for k from 0 to n, kinetic of AK dot k factorial m minus k factorial. Okay, and then if you divide both sides, so notice that this is n factorial. Divide both sides by n factorial, then you have summation for k from 0 to n, kinetic AK dot k factorial n minus k factorial n factorial less than or equal to 1. Or if you want some concise form, that will be divided by n choose k less than or equal to 1. And then you have summation for k from 0 to n, ak divided by, you enlarge the denominators to n choose n over 2 floor. Okay, so here you use unimodulity. Okay, the reason is that actually we uniform the denominator. So that gives you the total summation or coordinate or AK is less than or equal to n choose n over 2 floor. So we are done. Okay, actually in the following, we will actually generalize Sperner theorem to arbitrary pose set instead of just the sets with the order induced by the inclusion relation. Generalize to partially order the set, or pose set in short. So to do that, actually we slightly generalize the concept of train. So for a non-empty finite pose set, you can try to test if the concept still works when you get rid of the finite assumption. But to make life easier, in the following, we will assume all the pose sets are finite. Okay, and the C is Chi C. So here Chi C is a subset of X, is a train if for all X, Y in Chi C, either X less than Y or Y less than or equal to X. And then similarly, Chi A is called an antitrain if for all X, Y in A and X different from Y, X not less than or equal to Y, and Y is not less than or equal to X. An immediate remark is as follows. If you have a train and an antitrain, then they at most have one common element. Because if you have two, then by the property of train, they should have there's an inclusion relation, but according to the property of antitrain, there's no inclusion relation, so it's a contradiction. Okay, and the example is that, of course, a previous inclusion relation, the trains and antitrains defined by inclusion relations is a special example for this definition. We just realize order less than or equal to be the inclusion relation. And next, we give some other examples. Suppose you have integers 1 to 10, and then let order vertical line be defined by division. Okay, then Kyle A equals 4, 6, 7, 9, 10 is an antitrain. This is because for there are no elements x, y in A. X and y are different, such that x divided by y is divided by x. And C defined by, so here we use by a slightly abusive notation, we use the following one. 1 divided by 2 divided by 4 divided by 8 is a train of size 4. So here I would like to define some notion which we will use slightly later. The size, the cardinality of Kyle C is called the size of C. And similarly here, cardinality of A is called the size of Kyle A. Okay, also we claim that first, there is no antitrain of size greater than or equal to 6. And secondly, no train of size greater than or equal to 5. So in other words, Kyle A defined above is a maximum antitrain. Kyle C is a maximum train. So proof, so for first one, consider the following trains: 1, 2, 4, 8, 3, 9, 7, 5, 10, 6. So here let's call it X1 train, X1, train X2, train X3, train X4, train X5. Then noted that the total set X is a disjoint union of X1, X2 all the way to X5. And for each antitrain, if you consider the intersection with Xi, then it consists of at most one element. Otherwise, you will have, this is by the example here, by the remark here. So by remark above, we made above. Okay, then the coordinate of A is coordinate of A intersect X axis total set. This is summation intersect of with xi, so less than 5. And 2 is, for 2, just noted that things, so let A1 divided by A2 divided by A0 divided by A1 divided by A2, A3, all the way to A, let's see, AM is a train, then AI plus 1 divided by AI, at least 2. Then AM divided by A0 is AM divided by AM minus 1 times AM minus 1 divided by AM minus 2 times A1 divided by A0. So it's at least 2 to m's power. Okay, and since AM is bounded by 10, we can draw the conclusion. So here noted that remark. Actually, from the proof of claim 1, we noted that the property of antitrain kind of encoded in the property of trains. So the question is, what is the relation between trains and antitrains? And very unexpected and interesting property is that answer. If there is a train of size r, then x can be partitioned into r parts. Are antitrains, but no less. And similar result hold when you replace all the trains by antitrains and antitrains by trains. So this is quite astonishing property. And actually, one of the direction is quite easy. So that is one direction is easy. That is, if there is a train CO size R, then X cannot be partitioned into less than or equal to R minus 1 antitrains. And the same result holds when you replace antitrains by trains by antitrains. This is due to the fact that the intersection of any tree with any antitrain consists of at most one element. Okay, so I leave this to you. To understand this. Next, we will prove the other harder direction. So let x less than or equal to be a finite, partially ordered set be the largest size of a train. Oh, sorry, here I missed one condition. There is a how to say? So here you should input a train C of largest size. Largest size. Sorry, I made a mistake. Yeah. Oh, a train. Then X can be partitioned into R, but no fewer antitrains. So one direction is easy, so it suffices to construct R partitions to show that X can be partitioned into R antitrains. And let X1 be X and consider the set of all the minimum elements. And then A1 is an antitrain. Otherwise, if you have, for example, x1 in A1, x2 in A2, such that x1 less than x2, then x2 is not a minimum. Okay, and then let x2 be x1, get rid of A1, and A2 be the minimum elements of x2, then A2 is an antitrain. And you continue until we have xp is non-empty, but xp plus 1 is empty. If you write down the set in terms of order in the following graph, then we may have a better understanding. So next, we want to estimate P. So in other words, we need to know what's the relation between P and R. So notice that in this order means so let me explain a little bit about this graph. For all elements, let's see, xk in AK and xk plus 1 in AK plus 1, we have xk plus 1 greater than xk. Not greater than xk. Wait a moment. Can xk plus 1 cannot be less than or equal to xk. Okay, now claim. So notice that so far we haven't used a property that we have a maximum, the largest size of a train in X is of size R. Next, we are going to construct a train from the data of antitrains. So for AK in a capital AK, there is an element AK minus 1 in AK minus 1, such that AK minus 1 less than or equal to AK. So proof, we prove by contradiction. So otherwise, AK is a minimal element of xk minus 1, which is defined by xk minus 2 get rid of so x get rid of A1 union A2 union all the way to A k minus 2. Yes. Okay, and so you can verify it by yourself, because suppose you have AK chosen, and when you choose AK minus 1, you don't have such element. That means all the element of AKS1 so all the element AK minus 1 not less than or equal to AK. Then you have then AK is minimal. Okay. It's not hard, but probably you need to think about it. Okay, so this is a claim. And based on the claim, then we can choose a train A1 less than A2 less than all the way to AP. Then since this is a train, then we have P should be a number less than or equal to R. And on the other hand, we already have a partition. X is A1 disjoin A2 all the way to AP. Then we are done. Next, we're going to discuss a more interesting version, which is a dual version. And endorse the name of dual words theorem. So everything is similar. You just exchange antitrain and trains in your statement. So let x less than or equal to be a finite poset or partially ordered set, and let M be the largest size of an antitrain, then X can be partitioned into M, but no fewer trains. So similarly, it suffices to show that X can be partitioned into M trains, and we will prove by our induction on the total number of elements in X. Number n of elements in X. And if n is 1, then theorem holds trivially. Now assume that theorem holds for all n greater than 1 and less than or equal to m minus 1. Oh, sorry, not m minus 1. Okay, so let's fix the notation a little bit. For all n greater than 1, less than or equal to n naught, consider n equals n naught plus 1. Okay, and we can also assume X, M is the largest size of an antitrain in X. And here by assumption, the kinetic of X is n naught plus 1. We decompose the problem into two cases. The first case, suppose antitrain of size m has a simple structure. That means suppose the antitrains of size m are either we call it MA, which is set of all the maximum elements, or MI, which is all the minimum elements. Later on, we will show that actually this is a slightly difficult case. Although the structure of the antitrain is more transparent, so we make the following claim. There is a minimum element x and a maximum element y such that x less than or equal to y, and x equals to y is allowed. I will first prove this, and then we explain why we want to make such a claim. So without loss of generality, we can assume that there is an antitrain MA of size M whose elements are all the maximal elements. Take a minimal element x of capital X. So Y exists because it's a finite pole set. And if X is not less than or equal to Y for all Y in MA, then if you consider the set X union with MA, this is an antitrain of size M plus 1, which is a contradiction. Okay, then we choose such X and Y and consider the subset X get rid of XY, and then claim the largest size of an antitrain in X get rid of XY is M minus 1. And proof, it's easy to see that antitrain at least M minus 1, because we have MA theta defined by MA get rid of Y. So M theta is an antitrain with size M minus 1. Okay, and now suppose if the claim doesn't hold, then there is an antitrain A theta of size M in the subset. However, such AI is also a train in X, and since it's of size M, it's also maximum, then by assumption, A theta is MA or MI, which is a contradiction because we already delete X and Y. Okay, then by induction, X get rid of small x and small y is a set of n now minus 1 element. And the size or the larger size of the train is m minus 1, then we can partition it into m minus 1 trains. Say k is a train. Then x is train C naught defined by xy and the union C1 disjoint union C2 all the way to Cm minus 1. So totally you have partition x into m parts. Okay, now let's look at case 2. So case 2 is that there is an antitrain of size m that is neither ma nor mi. So ma and mi are defined above, which are set of maximum elements and a set of minimum elements, respectively. And define A plus to be all x such that x is greater than or equal to some A in the antitrain A, and the m minus is similarly defined as long as you have some A greater than x. If you draw a picture, you have this is your A. And what is A plus? A plus, A plus is a set consisting of all the elements with a flowing line to A. For example, so we draw a line if x1 is greater than A1, here A2, A3, x1 prime, x2, x3. Okay, and similarly, this is A plus, and similarly A minus. The point of A minus can be connected to A by the inverse inequality. So here, for example, let's call it x3 theta, x3 prime theta, x1 theta, x2 theta, and if we write down the inequality, that will be x2 theta less than or equal to A2. When you satisfy the less than or equal to inequality, we draw a line here. Less than or equal to A3, less than or equal to A3. x3 greater than or equal to A3, x1 greater than or equal to A1, x1 prime greater than or equal to A1, x2 greater than or equal to A2. Okay, and actually we use this idea quite a lot in mathematics already. Let me make a remark. So this is actually related to Morse theory. smell, mouse, written, complex. So A part is called stable manifolds. A minus part is unstable manifolds. A is called fixed point set. You can search online what does this mean. It's quite interesting. Okay, if you learn such no such picture, then later on it's easier for us to understand how we construct a train in the total space X. Okay, now we can list several properties satisfied by A plus and A minus. So first, A plus is not X for there's a minimal element of X not in A. Okay, and secondly, A minus is not X, for there is a maximum element of X not in A. And thirdly, A plus intersect A minus is A. This is if B is a common point of A minus A plus, and B is not in A, then there exists A1, A2s in A such that A1 less than B less than A2, which is a contradiction because we assume A is an antitrain. And fourthly, the union is X. So for if X, a small x is an element in X, get rid of A plus, A minus, then we have X is not greater than or equal to A for all A in A, and X is not greater equal to A for all A, not less than or equal to A for all A in A, then X union A is an antitrain. So that's a problem. That's a contradiction because we assume A is of maximum, the largest size. Okay, then by induction on A plus and A minus respectively, we have the decomposition okay, and then define CR minus union CR plus. Okay, here we also assume CR minus intersect CR plus is non-empty. Then CI is a train. X is disjoint union of M train. So here actually we use a gluing argument, that is after you take a partition, for each point A1 in A, there will be one train connecting above and connecting down. Then you glue them up together, which gives you, for example, this one, which gives you a long train. Okay, let's say I. And the remark is, here, as soon as you have non-trivial cut A, then the induction is clear, quite geometric, but so case 2 is quite geometric. And the case 1, since the cut doesn't work, you need to use some other argument. It's actually an exceptional case. Okay, then we are done. And the next very interesting question is how to actually construct the partitions according to the number n choose n over 2, or the least number r. So here we give one algorithm. So the largest size of an antitrain, in general, is quite difficult to do that. Or you just use the argument in the proof to do the construction. The algorithm is not that clear, but for the previous studied inclusion relation, we have a much explicit construction. So we already know that the largest size of antitrain on Px, so here Px is all subsets, the set of all subsets of 1, 2, all the way to n, is n choose n over 2 floor. And then by Dewars theorem, Px can be partitioned into n choose n over 2 floor trains. Okay. Then explicit construction. So first, when n is 1, of course, you have a natural train, empty set contained in 1. When n is 2, we need to have 2 trains. When n is 3, we have 3 trains. Okay, and suppose the partition when n is k is known, and for n equals k plus 1, we can construct in the following way. So first, actually here, each train in n equals k generates 2 trains in the case n equals k plus 1. So notice that all the trains when n equals k plus 1 is generated from trains when n equals k. So how to do that? Firstly, we can attach at the end of a train in when n equals k, the subset obtained by appendix k plus 1 to the last subset of the train, so the input train. And secondly, we appendix k plus 1 to all subsets and delete the last subset in the train. So let's run the algorithm for k equals 3. So when n equals 3, you have 3 trains. First one is empty set 1, 1, 2, 1, 2, 3, and then run the algorithm once. The first method is attaching to the train a subset contained by appendix k plus 1, 4 into the last subset. So attaching 4 here. So then you have this train. And secondly, this is the first case. And secondly, because k plus 1 is 4, you just add 4 to each each subset in the train. One contained 4 contained 4 1, 2, 3 1, 2 1, 2, 3, and then for the last one you just delete it. Okay, then you have this. You generate 2 trains from this train when k equals 3, and then of course you have another train 2 contained in 2, 3. Then you can generate 2, 2, 3, 2, 3, 4, and then you have 2, 4, 2, 3, 4, and drop the last subset. And for 3 contained in 1, 3, similarly you have 3, 1, 3, 1, 3, 4, and 3, 4, 1, 3, 4. We drop the last one. Okay, and so that's it. And the remark is, actually this construction is quite interesting. It shares the following properties. Therefore, some people also call it symmetrical train partition. So firstly, increased by 1 element in each train for the adjacent subsets. That makes our train more economic. And secondly, the average size is n over 2. It might be a fraction, for example, 3 over 2, but if you take average, it's n over 2. And thirdly, therefore, by these 2 properties, you can count there are choose n over 2 floor trains in total, because each train contains a subset with cardinality n/2 floor. Okay, so there are totally n choose n/2 floor subset with a cardinality n/2 floor. Then totally you have so many trains. Okay, I will stop here.